Now we're going to start this unit with two theorems. One will be the mean value theorem, but a very special case of the mean value theorem is actually the Rolle's theorem, so we're going to go over that one first, now that I'm actually recording. All right, so I'm going to start with a picture so you can kind of understand what we mean by Rolle's theorem. So in the beginning, when you're learning calculus, we love to put theorems around items that seem, like I said, kind of common sensey, but that's a good thing. So if we had two values of x, okay, a and b, for some theorem, for some function f of x, okay, and these two theorems, I didn't think I recognized him. He was not in our class, right? I'm like, I don't recognize him. Okay. I guess he finally decided to leave. So what's going to be so special about these points A and B? We're going to make it so that f of A is equal to f of B. So part of learning these theorems is understanding, well, what does that mean? If I were to picture that, if you're not already looking at the notes and picturing it, if I were to picture that, what does that mean that f of A is equal to f of B? So whatever f of A is, right? Oh, f of B has to be the same thing. So that's what means f of A equals f of B. So basically we have these 2 points where they have the same value, the same y value essentially. If that occurs, in order for a function, no matter how it's drawn, and I'll draw it differently than it's drawn on the thing, it doesn't really matter, unless that function is linear, and we're not talking about a linear function would go straight through those points as a horizontal line. We're not talking about a linear function. So if a nonlinear function is drawn, wouldn't it make sense that for that nonlinear function to go through one of those points and then to also go through this point, it has to at some point turn around like that, right? Right? Which means there needs to be some value c, right, that is definitely between A and B, some value c that's between A and B, such that f prime of c must equal what? So whenever you see f prime of c, you're thinking what word in your head? Derivative. There has to be, in order for that function to come down and turn and go back, and you'll see if you're looking through the notes, the function goes up like this. Same idea. It's got to turn and come back. No matter which way it goes, there has to be a value c such that the derivative at that point must equal what? Yep. In other words, there's some horizontal line that could be drawn to that. 0. So you can think of it this way. If f of A equals f of B, there must be a point C in the middle that ends up being a max or a min, because that function has to make that turn. All right, in the picture I drew, that function ends up being a minimum, right? But it could be a function, I'll do it in another color. There has to be at least one value C. Now, when you say at least one, that means there could be. So let's take a look at, I'll draw another function in green. We'll get a little Christmassy here. If I do another function in green, I go up. Oh, I can turn, I come up. Boom. just to get between A and B, there has to be at least one value C where f prime of C equals 0. Okay? At least. See, there's an example there where there's 2. There could be 1. But there has to be at least 1 because that function has to make that curve. And when it makes that curve, it creates a max or min. And when it creates a max or min, the derivative at C must equal 0. So now that you've kind of seen the picture, let's write the theorem down. So here's the theorem. We'll try to write it and leave the picture up there. There we go. So the actual theorem. So what do you think must be true about f itself, first of all? F has to be, in order for this to work, what do you think? Say it. It definitely has to be a function. And what kind of a function? It's got to be continuous, right? So yes, when we label something f, we define it as a function. So let's start by saying let f be continuous. Because I want you to realize these words are not just thrown in there to make the theorem sound better. There's reason for every single word in a theorem. On a closed interval AB, okay, because you have to be at A and B, it's because we're using A and B as part of this. But when we talk about being differentiable, we actually, interesting enough, can't be differentiable at the endpoints. So it's differentiable on the open interval AB. So it has to be continuous on the closed interval, differentiable on the open interval. With, and the other major condition for it to be defined as Rolle's theorem in the first place, f of A equaling f of B. So we set up all of our parameters now. Continuous on the closed interval, differentiable on the open interval, and f of A has to equal f of B. So what does the theorem state? There is at least one point C such that it's like my pen is running out of ink, but it can't run out of ink, such that f prime of C equals 0. Okay, so that's the theorem, that's the picture, that's the words around it. There is at least one point C such that f prime of C equals 0. So again, if you go through the notes, you'll get a lot of accompanying pictures that I'm not going to go through in class because you can kind of do that on your own. There's all sorts of pictures of functions. And there's pictures of why do we require continuity. I think that one's kind of, you see that at this point, because if it wasn't continuous, why do we make it continuous and differentiable? So a non-continuous function isn't going to work. For a non-continuous function, you could have something crazy like, I don't know. You know, if you don't have continuity, you can't assume Rolle's theorem is going to work. And if you don't have differentiability. So what does that mean? Do you remember what it looks like when a function is continuous but not differentiable? 0. I said my pen, it's like my pen's running out of ink, but I'm writing on a computer. That can't happen. Sorry. That still doesn't look like a 0. So do you remember? You can be continuous, but not different. I think I just drew it, right? Did you watch that? So in other words, here's something, you know, a function that looks like that. That's not going to work. But it doesn't fit our parameters because we're not differentiable at that middle point. So you don't have to worry about that. So there's more pictures of that in there. So how can you show that Rolle's theorem, or how can you apply Rolle's theorem? We'll start with a simple thing. So let's suppose we had a function. And I want you to find an interval where Rolle's theorem applies. That is not a negative. That is, you see, it keeps, there you go. Find the I. I stands for interval. Find the interval on which Rolle's applies. So now, okay, so first you find the interval, then you're going to find all values of C. So remember what we said. The parameter to find this interval is f of a has to equal f of b. They've got to come out to the same thing. When you're working with polynomial functions, what's the easiest thing to set something equal to? Where you could end up with multiple values of x where it equals this 0. So the best thing to do to find this is to set your function equal to 0. You can try other things. You can try setting your function equal to 1, equal to 2. You can set your function equal to anything you want it to be. And then you're going to get all the x values that makes that happen. But the easiest thing to set it equal to is 0. So we're going to find all values of x such that this function equals 0. So our function is x cubed. Okay, but again, you can find any interval you want. This is the easiest way to find an interval. So let's get some C values. In other words, let's find some values such that they all equal 0. How do I do that? See, a lot of this stuff goes back to what you learned in basic algebra, right? You've got something, a higher power, meaning not a linear function. See, if it's linear, it's easy. You just solve for x. We are solving for x, but it's not linear. What do you need to do? Yes. You get a factor. It's set equal to 0. See, if it wasn't set equal to 0, you'd have to rearrange it to get it equal to 0 and then factor. So you got a factor, so take out your x. And keep factoring. Please tell me this is factorable. If not, that's okay. Because if it wasn't, we would know what to do, right? Because if something's not factorable, what do you use? You could use quadratic formulas. You could use all these other things. So we have x minus 5 and x minus 2. So remember what this means. This means, hey, f of 0 equals 0. F of 2 equals 0. F of 5 equals 0. All right? That's what this means. And that's what you got to, what does that mean? Oh, it means all those F of things. I only need in it one interval. One interval has 2 endpoints. So we can use 2, 5. Let's take 2, 5. Doesn't matter which one you really pick. I'm just going to pick 2, 5. But you have choices. Here it is. You just have to find an interval, and you've got to find a C value in that interval. So if you pick 2, 5, you're going to get how many C values, do you think? Probably 1. If you pick 0, 5, how many C values are you going to get? Probably 2, right? Because you're going to get a C value between 0 and 2, and you're going to get a C value between 2 and 5. So, however you want to do it, if you're just asked to find an interval, whatever. We'll just pick the largest one. We'll find all the C values. So we'll pick the largest interval. So our interval is going to be 0 to 5. So now, how am I going to get the actual C value? We now know that f prime of C has to equal 0 at likely 2 points between 0 and 5. How are you going to find those 2 points? What do we need to do? It's kind of written here. What does this say? So what do we need? Yeah, you need derivative. So through part of what we're doing over the next couple of days, you got to know when you're setting the function equal to 0 and what meaning that gives you, and when you're setting the derivative equal to 0 and what meaning that gives you. Okay? So to find our C values, well, we need f prime of C equal to 0. So let's get our derivative real quick. All right, so now we're going to take the derivative, which is what? 3. We can do this one quick. Okay, this is the one where we might have to what? So when does that equal 0? Real quick, how you can tell if you can factor a function, do the a times the C value, 3 times 10 is 30. Are there 2 factors of 30 that add up to negative 14? They would both have to be negative. 5 and 6 aren't going to get you to 14, correct? Is there anything that's going to get you to 14? Can you factor that? No. This is going to happen. It's going to happen when you're working on your homework problems. You have technology available to you. Yes, you can go through. You can try completing the square. That would be messy because of all the fractions you're going to get. I'll tell you right now. You can use the quadratic formula. Go right now on your phones. You got smart, unless you got to pay for data or something like that. If you got like free data, go on your smartphone. Seriously. Find yourself a quadratic equation calculator. Okay, you're in calculus now. When you're doing this math lab homework, right, and you got to sit and use the quadratic formula on a function, what do you usually do? Say, I ain't doing that problem, skipping to the next one. Don't do that. When I'm on a test, I'm going to give you stuff that's factorable because it takes too much time. Go on your calculator. Literally look up quadratic equation calculator. Find a website that'll do it for you and give me the roots of this function. So go on your computer. Those who have a computer open, those that have a smartphone. Graphing calculator will do it if you graph the function and find the zeros. But go ahead. and take a minute, use any technology you have available in front of you right now, and tell me approximately what those values are that cause that derivative function to equal 0. Okay, because I don't want you to get caught up when you're stuck on a problem because of something like this, right? Did you find something? You should be able to find something. What'd you get?
I got 3. X equals -7/3 plus or minus square root of 19/3.
-7/3 plus or minus square root of 19/3? Yeah. So, did anybody else get that? Now, even if you get that, you can now get your calculator and work that out, right? Did anybody's graph calculator give them a decimal? What'd you get?
I got 0.88, 3.76,
So 0.88 and so my guess is if you work out the top one, you're going to get those two values. All right. So again, this is when you can use technology, ChatGPT, though that thing's always down now. I wouldn't suggest that one. There's better stuff out there for math. Okay, to do some of these calculations, I'd rather you do that than skip to the next problem because you didn't feel like working out the quadratic formula. Does that make sense? All right. So all we're doing is verifying. These are our values of C. These are the places where your f prime of C equals 0. So that means f prime of 88 equals 0. F prime of all you have to do in your last step is you're verifying the theorem. Do these values fall in that interval? Yes. 0.88. Apparently, I can't work on the bottom of my computer screen, so I can move that up. And 3.79 are in 0, 5. Done. Wait a minute. My computer screen's not letting me work on the when it's scrolled down at the bottom. It's probably my screen losing it because I write on it so much. Okay? So that's just verifying Rolle's theorem. That's all that is. So now, Rolle's theorem is a very, very specific case of the mean value theorem. So now we're going to broaden this. And we're going to take it out of a very specific case and we're going to turn it into the mean value theorem. All right, and the mean value theorem is something you see a lot. It has a nice shortcut, MVT. You'll see MVT. So the mean value theorem says, okay, that's nice, but let's kind of make this more generalized. I'll still have a function, right? There's my f of x. I still need my a and b values. Let me offset them a little bit more. Let's put b over here, okay? But this time, okay, we're going to do it so they don't have to equal each other. F of a does not equal f of b anymore. All right? This one's a little trickier. So you have an f of a, and you have an f of b. And here's kind of what the mean value theorem says. Well, if I take a secant, this goes back to our secant and tangent lines. Remember those? If I draw a secant line from or through A and B, Okay. So we all remember how to find the slope of that secant line, how you find the slope of any line, right? How do you find the slope of the secant line? Based on what I have on the board. How do you find the slope of any? It's changing y over changing x, right? So what's the slope of the secant line? F of b minus f of a over, okay, that's just your formula, basic formula for slope, okay? So now, the mean value theorem says between A and B, there has to be some value C there's got to be some place between A and B where there's a tangent line that has that exact same slope. So there's got to be some value C where f prime of C is the same slope of the secant line between A and B. So in other words, that function, as long as it's, guess what's going to have to be one of the priorities. It's got to be continuous. It's got to be differentiable, right? Then, in order to get from this point to that point, you have to hit a point somewhere where the derivative of the tangent line at that point equals that slope of the secant line. So let's put that one in words. I'll put it off to the side because I don't want to go down too much. So here's the theorem. If so again, f is continuous on a closed interval. And differentiable on the open interval. Then there's at least one point C such that f prime of C equals that slope, f of b minus f of a over b minus a. We'll do two quick little examples, and then we'll be done with mean value theorem. So we'll do one where, again, this time, instead of with Rolle's theorem, you can be asked to find the interval because you know those values, f of a, have to equals f of b. So you can set them equal to a number. With the mean value theorem, you'll be given the interval to work on. All right? So here's the problem I'm going to give you. Let's verify it's, again, like always, I love technology and then it doesn't work and it breaks and now I'm getting like crazy lines all over my thing. Let's verify the function f of x equaling x squared minus 3x plus 1 satisfies the conditions of the mean value theorem. Mean value theorem on the interval -2, 2. Okay, so to satisfy these conditions, we first need to figure out what that slope is. All right, you got to know the slope. So we need the slope of that secant line. So 1, you need the slope of the secant line. That goes from -2 to 2. All right, so to get the slope of the secant line, the formula is right there. We need to find f of -2 and f of 2. That's putting into the basic function. So do that calculation for me real quick. Find f of -2. Oh, come on, we'll probably do that one in our head, right? 4 plus 6. Is the first one 11? 11? We go with 11 on the first one? Don't let me do math in my head. It never works out well. Let's do the second one. 4 minus 6. -1? No. -1? -1? Everybody? Don't only let like 2 people do math. You need like at least 3 or 4 to have a consensus. Okay. So now I can get that slope. So this is slope of that secant line is going to be, so we're going to do, our B value is 2. So f of 2 is -1 minus f of 1. F of -2 is 11 over 2. Oh my gosh. All right, do the math. -3? I think I did the math right. Check my math. All you do is basic slope. You're given 2 points, right? Because it's a secant line, so it's a linear line between them. Just find the slope. Okay, so what does this mean? To satisfy the mean value theorem, we have to find a point C such that f prime of C equals what? -3. So we need a C value where f prime of that C value equals that slope. All right, well, to do that, what do you think I got to do first? You need, yeah, that f prime is pretty important. You need the derivative of our original function. So first, we need to find f prime of x. Which is 2x minus 3. 2x minus 3. Right, because the original function was x squared minus 3x, so 2x minus 3. Oh, go ahead and set that equal to 2. Don't set it equal to 0 because we're not doing Rolle's theorem. I almost said it. We're going to set it equal to -3. And all you're doing when you're verifying something like this, we're going to get a value. We're checking if this value actually falls in that interval. That's all you need to do. So what do we get? 2x x, wow. 2x equals 0, x equals 0, right? And you check, yes, question?
Why are you setting it equal? Why are you setting it equal
Because the theorem is when you get this slope, there's going to be a value in between there where the function equals that slope. It has the same exact slope, where the derivative equals -3. See, in Rolle's theorem, we were specifically making, there was no slope. Every line was a horizontal line. So that's why mean value theorem, or let's put it this way, Rolle's is a very special case of the mean value theorem, where the lines are horizontal. Here we got slanted lines. So we have to figure out what that value is that we're going to set it equal to, okay, by finding the slope of the secant line. You set it equal to 3, you find your x, and go, yep, I'm good. I love check marks. Because, and you got to write that statement as to why you have verified it. Because 0 is in -2 to 2. 0 falls in that interval. So you're not solving anything here. You're just verifying. You're showing me the work that, yep, it's there. There it is, and it's in the interval. Okay? Verify is something you did in pre-calc 2 a lot with trig identities. You didn't solve them. You verified that they were true. That's what you're doing with this. A quick silly example of the mean value theorem. Ready? You're at rest. You're driving your car. You're getting onto a really busy highway. Your car is stopped. Okay? So we're starting off with our car stopped, about to get onto a busy highway. All right? So your car is at rest, getting on a highway. Now here's what happens. Because they let, you know, the patrol officers are out and really need to make a lot of money this month. So they radio down, hey, I got this car. Looks really like it's going to be a speedy car. So I'm going to give you its license plate, all right? And the radio's ahead to its buddy down the highway. And that other officer is 28 miles down the highway. And that officer clocks you at 60 miles an hour. And you're like, cool. I was at rest when I saw the first cop car, so I'm good. I'm only doing 60 miles an hour when I see the second cop car, so I'm good. But here's the problem. Only 19 minutes go by. How does that second officer know you exceeded the speed limit of 65 miles an hour? It used calculus. All right, it didn't. It probably has a little formula real quick that it knows to do. So let's put this in the context of what we were doing. So I like to draw graphs. I like to kind of think of it this way. You know, you're driving along, your speed's going up and down or whatever, but you're starting at rest. What does that mean? That's 0, 0, right? So we're talking speed, you know, so the speed you're going, everybody remember this? If distance equals rate times time, then rate equals distance divided by time, correct? Okay. So at time 0, you've gone 0 distance. And then at 19 minutes, How far did you travel? 28. Okay, so here's the idea. That is a 19. Okay, 19 minutes later in time, you made it to 28 miles. Everybody see that? But you were only clocked to going 60 miles an hour. So what we're going to do is the idea of the mean value theorem is if we can figure out this rate, right, of that secant line, that means somewhere in your journey, you went that speed. So we're going to figure out what that rate is. Now, there's an issue with this problem. We know things in miles per hour, right? With speed. 19 minutes is not. So what do you have to do? Take your 19 minutes and convert it to, yeah. You can leave it like that. Leave it as a fraction. We're going to use a calculator in a minute anyway. Does that make sense? So instead of 19 minutes, we're going to call it 19/60ths of an hour. Okay? So let's find our slope. Well, there's really not a lot you got to do here. F of 19/60ths is 28 minus 0 divided by 19/60ths minus 0. So it's 28 over, which everybody knows means what? Right? Doesn't that mean that? Yeah, all right, give me the number. Yep. 88 point what? They used to do this on the Turnpike, New Jersey Turnpike, through toll booths. They would have your when you used to go through the New Jersey Turnpike, you used to have to get like things. Now they got Easy Pass, but they can still get you because they know how long it took you to get to one toll booth to the other, and if it was, they can tell how fast you were going at least one point in between.
Isn't it the same thing that they do with airplanes?
Yep. Yeah. They can clock you if they really want to get you speeding. They can use calculus. This is essentially the mean value theorem. That's all it is. Because there's a secant line that says, hey, that means somewhere in between those 19 minutes, you had to have been going 88 miles an hour. Had to. Okay? Mathematical proof, you got yourself a ticket. Anyway, there's an application. Simple one. All right? So that's everything with those two theorems from 4.2. Now, this next unit, 4.3 and 4.4 kind of go together. And ultimately, what our goal is to take any function, take everything you learned in algebra and pre-calc, and everything you've learned now in calculus with derivatives, and you're about to go over with derivatives now, to perfectly graph any function without technology. And then just use your technology to check it. So 4.3 is all about what the derivative tells us. Again, there's a lot of nice pictures and graphs, and you should really go through these notes. Ultimately, there's two things I want you to get out of this particular chapter. The first thing is called the first derivative test. The first derivative test we actually talked about on Thursday a little bit. We're going to go through, hey, what does the first derivative tell us? We found out in Thursday's class that the first derivative, when you set it equal to 0, doesn't it give you possibly your mins and maxes, right, of your function? All right. It will also, we talked about, tell you when your interval, when your function is increasing and when it's decreasing. So first derivative test in a nutshell, and we're going to go through it in a lot more detail, can get you information about possible mins and maxes, and it tells you when f of x is increasing and decreasing. So we have first derivative test, and guess what the second one's called? Want to take a guess? Second derivative test. The second derivative test. So that's nice to know if your function's increasing or decreasing. But increasing and decreasing can mean different things, right? So for example, that's an increasing function, correct? Well, isn't that also an increasing function? These are both increasing. What's different about them? You can kind of visualize it, right? So there's a word for this. Do you see it? Like if you think about something holding water, that can't hold water, this can hold water, right? Okay, there's a name for this. Concavity. This will give you important information. The second derivative gives you important information of when your function is concave up and when it is concave down. So concave up, it's going to look like this. Concave down is going to look more like that. Concave up can also look like that. Concave down can also look like that. There's all different things, but you get the idea. Concave up, concave down. So if you take everything you learned in algebra and pre-calc. So what do I mean by that? Oh, things like intercepts. You know how to find intercepts. Symmetry of a function. Domain of a function. Okay. And then you put in these first and second derivative tests. You will get a clear picture of what your function is. So first, we're going to look at the first and second derivative test. So let's take a look at that first derivative test, which we kind of done already. So this is theorem 4.8. So we have some assumptions. Let's assume, of course, f is continuous and differentiable. On an interval that contains C. C just stands for critical points. Remember, we find those critical points, and then we determine if those critical points are actually max and mins and everything else. Critical points are important. C stands for any critical point. So do you remember when critical points occur? We look for when it's equal to 0 or the function doesn't exist. That's a critical point. When the function equals 0 or the function doesn't exist. So here we go. Here is the first derivative test. If f prime, if the first derivative, this is one of those things where you're going to write all this down, and when you see an example, it's going to make a lot more sense. So if f prime changes sign, and I had you doing this in the lab. We did a little last Thursday. Changes sign from positive to negative. Okay, so I want you to visualize that. F prime, that means it's the slope, right? The derivative. So if the derivative is first positive, that means it has a positive slope, right? And then all of a sudden it changes to a negative slope. What kind of value do we likely have at C? It's going positive and then negative. So what do we have? A local maximum. Okay, so if f prime changes sign, from negative to positive. So we're going to do the same thing, but now it's changing sign. It has a negative slope, it's going down, then all of a sudden it switches and has the positive slope. What do you have? A local minimum. If it doesn't change sign, then there is no local extreme value. If it stays positive or stays negative, we have those points of inflection that occur, okay? If there is no sign change, then there is no local extremes. Likely a point of inflection. Likely a point of inflection. And that's something, if your graph is going like that. Do you see it? If your graph looks like this, positive, positive, positive. Oop, I'm hitting f prime equals 0. Positive, positive, positive. That's what I mean by that. Okay? So that's your first derivative test. We're going to put together the first and second in this nice chart. That's what I'm leading to. So let's do one example with local, with first derivative. Please, again, look through these slides. There's lots of pictures to help you understand this. I just don't have time to go through all that in class. Please look through them. But let's take a look at one quick example. I hope. I know there's one of these on here, but we all know how to use quadratic equation calculators now, right? Because I know there's one of these that doesn't factor, and I can't remember which one. All right, let's look at a quick example. F of x is 12x cubed minus 12x squared. It's 12x plus 12. Okay. Find the intervals where it's increasing and decreasing. So when you're asked to do that, you're doing a first derivative test. When you want to know when your original function is increasing or decreasing, that's key to first derivative test. So to do a first derivative test, well, let's figure out f prime. What's f prime? Right? You got to get those critical values. So that's what we're finding. Let me put some steps in for you. Find your C's. Your C's are referred to as your critical values. Right? So critical values occur when it's equals to 0 or it doesn't exist. This exists for all x's. There's no, you don't have to worry about it equal to 0. I mean, you don't have to worry about it not existing. Set it equal to 0. I'm going to take out a 12. Please make sure my math is correct as I do this. I'm going to take out a 12 to make this easier, right? The 12, you can divide 12, the 12 goes away. Does everybody see that? If you divide both sides by 12, the 12 is gone. Negative 3 and 1. Yeah, this factors. So 3x, 1 and 1, and I think that's negative and that's positive. Check that works, right? Negative 3x plus 1 is negative 2, correct? 1, 1, yep. So what are my values? Good. I'm doing this a certain way because that's what's going to lead you. Is I want you to think of this as a number line. With my critical values placed neatly on that number line. Okay, makes sense? Get your critical values because this is going to help you when you put it all together. All right, we need to determine what's happening on these intervals. These critical values split it up into 3 intervals. Remember, you don't care what the value is in the middle of those intervals. You only care if it's positive or negative, right? So here's the question. First interval. Well, this interval goes from what? Negative infinity to negative 3, correct? Is f prime of x positive or negative? So, is f prime of x positive or negative between negative infinity and negative 3? Just stick a number in. So, pick a number. Pick negative 1, right? You're testing any point in that interval. Question?
Is it negative 1/3, right?
Yeah, that's 1/3. Did it not look like 1/3?
Well, you said 3.
Oh, I just said 3. No, negative 1/3. Oh, I put it there. Sorry. Sorry. There you go. So pick a number in that interval, any number you want. Doesn't matter. It's a test. So what do you want to try? Negative 1? Let's try negative 1. Look at your derivative. Remember, f prime I like to leave it in factored form. It's much easier. And I go like this. All right, negative 1. Negative 1, we're going to test. Now, what's nice is you'll get used to doing this, and you'll just do it real quick in your head. You're not going to write all this stuff down. I'm writing it down for the notes. We're going to test negative 1. Well, if I plug in negative 1 times 3 and add 1, am I going to get a negative or a positive number? I don't care what the number is. I just want to know if it's negative or positive. I'm going to get a negative, correct? Negative 3 plus 1 is a negative number. What about negative 1 minus 1, negative or positive? What's a negative times a negative? That means this interval is increasing. Now you do another test. I'm not going to write all this down. Let's do a test for the second interval. My second interval goes from negative 1/3 to 1. So what would you test? Nice and easy. 0. You plug in 0, you are going to get a negative. You're going to get a negative. And my last interval, plug in 2. Are you going to get negative or positive if you plug in a 2? Well, 2 times, that's going to be positive. It's going to be positive, 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 right? You're done. All I wanted to know is what intervals is it increasing and decreasing? Your original function is increasing. So how would you write this out? Increasing between negative infinity and decreasing. Okay. That's our first derivative test. First derivative test simply tells you when your function is increasing and decreasing. And like I said, you got a bunch of examples there to look at in your notes. Now let's go on and move to the second derivative, because it's way more fun to put all this stuff together. So let's take a look at the second derivative. There's 2 parts to the second derivative. So the second derivative really talks about concavity. But the most important part of the second derivative is the test for concavity. Because when you go ahead and take the second derivative of that function, that second derivative is increasing when your function's concave up. That second derivative decreasing, the second derivative negative means your function's concave down. So let's suppose f double prime exists. That's your second derivative on I, some open interval I. Okay, same idea. If f double prime is positive, greater than 0 means positive, then f is concave up. If double prime is less than 0, it's negative, then it's concave down. Okay. And the last piece is if C is a point in I. So I want you to think about this for a minute before I write anything. So concave down, right? I'm going to write on the board. Concave down. Think of a max point for a minute. Right? this from, let's suppose I go from, A, C, B. So from A to C, all right? Isn't that an increasing function? But it's what? Concave down, correct? What's happening from C to B? What's my function doing? Now it's decreasing, but it's still what? Okay, that's concave down, that's concave down. So when you are, and this is what we're going to start to realize, if at your point C you switch from increase to decrease, we already know that means a maximum. But when you have a maximum, do you notice you remain concave down? All right, think about a minimum. What happens with a minimum? It's decreasing to increasing, but they're both concave up. Okay? So minimum values are going to be concave up surrounding that C. Maximum values are going to be concave down surrounding that C. So that means you're going to have the same sign, negative or positive on either side of the C. What happens when the sign switches for the second derivative? In other words, I don't care about increasing or decreasing. What if I go from, I don't know, and then I switch? Do I have a min or max? If I switch concavity from up to down or down to up, will I have a min or max? No. I have another one of those, what are those points called? Inflection points. All right. So if C is a point in I at which F double prime, because this is the second derivative test, changes sign. So when you see F double prime, you're thinking concavity changes. F double prime changes sign. Then F has an inflection point at C. F has an inflection point at C. So what I'm going to do is I'm going to take that same problem we did, but now I want to do the second derivative test on it, and I'm going to put these two derivative tests together. So let me write down what we did so far in our function. Okay, let me rewrite it. Our original function was that 12 craziness. So this was our original function. Was 12x cubed okay. Now to do a second derivative test, what do I need to do? Oh, first I got to actually take that second derivative. So let's take that second derivative. What do we get? 72x minus 24. Okay, we've already done the first derivative test, and we'll recopy what we did there in a minute. But let's just do our second derivative test now. We already did the first derivative test. Oh, so that means I got to take, all right, when does f double prime equal 0? So let's set 72 Can you just make that decimal for me, please? I mean, I guess we could be a fraction. It would be 8. 3, not 1/3? Is it 1/3? What is it? Positive 1/3? Maybe? Oh, cool. 1/3. Let's make it 1/3. Okay? So if we do this second derivative test on our own, it's only going to give us information about concavity. So if we do it totally by itself, same idea. What's nice is you only have one critical value now, right? So we only have two intervals. Here's 1/3, right? We only have two intervals to deal with. We've got this first interval, which goes from, all right, so look at your second derivative. Look at that second derivative. And think about putting, I don't know, 0 into it. You're going to get a positive or a negative value. What are you going to get? Right? If you test 0, then f double prime is definitely less than 0, correct? And what do we say happens when f double prime is less than 0? We are concave down. So this is concave down. What happens after 1/3? Yeah, it's going to go positive, correct? You plug in 2, 3, 4, anything else at this point greater than 1/3, your f double prime So that tells you the interval. So if you are only asked to find the intervals concave up or down, you're done. We can ignore the first derivative, go right to the second derivative, take the derivative twice, do the little test. We know our intervals. It is concave down from -infinity to 1/3, concave up from 1/3 to infinity. What I want to do is put these two together. And this is an important piece. When you put them together, because that's what you're going to do. You're going to do these two tests at the same time. To do that, it's important you set up the appropriate chart. What do I mean by that? All right. So we have f prime, first derivative test. And what were those values on the first? We already have it. Let's move up. Let's scroll up. What is it? -1/3 and 1. And it goes increase, decrease, increase, correct? So it's -1/3. I mean, you can stick 0. Just be careful because you don't want to use 0 for anything, but I use 0 to line you have to line everything up correctly. All right, and we said, okay, what was it again? Increase, decrease, increase. So that was the first derivative test of this function. It was increase. See, this is why I don't like putting the 0 in there. Do you see why? It confuses you. It makes you think you have another interval. You do not. So don't. Okay? Now, our second derivative test, all you need to do is put the numbers, line them up as best you can. What was our only critical value in our second derivative test? +1/3, right? So look at your graph. Where would +1/3 show up? About, you agree? And here we were, what was it? Concave down. So down and up. And this is the fun part. This really is fun. I promise. Watch what you do. I am going to draw dotted lines at all of those critical values, like this. All the way down, straight through them. Do you see what I mean by every critical value, there's a dotted line? And then I'm going to evaluate what's happening in all of those new intervals. So watch. First one, I'm increasing, but I'm concave down. I want you to stop and think what that looks like. I'm increasing, but I'm concave down. Doesn't that look like that? It gives you a place to sketch it out, to start to sketch it out. All right, then I'm still concave down, but now I'm what? In this little interval here, between negative, I know it's not a 13, negative 1/3 and 1/3. What's happening? It's a decreasing function, but it's concave down, so looks like that. Okay. You can start to see, hey, there's a maximum there, right? You start to see it. Next one. I'm still decreasing, but now I am concave up. Goes, right? Decreasing, but concave up. So you got to get these scenarios down. And in the last one, I am increasing and concave up. Right? Okay, so let's talk about what's happening at every single critical point we have there. First critical point, first green dotted line I come across, when x equals negative 1/3, look what is occurring there. We have a maximum value, right? You can follow the theorem or you can actually see it in the little sketches you made so far. Because you know you have a maximum, now is when you want to take the time to go back to your original function and figure out what that point is. So get your calculators out. I'm not doing it. In other words, we got to figure out what that actual maximum value is. Right now I have negative 1/3 comma something. You got to plug negative 1/3, and where do you plug it in? Base function. So you have to know when you're plugging things back in. So go to the original function, which was that 12x cubed, and go ahead and find for me let's get a couple people to agree. What do you get when you plug in negative 1/3 to your original function? We know it's a max value, so hopefully it's a pretty high number. 14.2. You got 14.2. Anyone else? You're just all waiting for everyone else to do the math. 14.2. Okay. And write down, oops, that's going to be a max. All right, let's go to our next critical point. Because this is a critical point, but what's happening here? Do we have a max or min at 1/3? No. What do we have? That's one of those points of inflection because you are changing concavity. When you change concavity at that point, you're going from down to up, you're going to end up with a point of inflection. So we still need to know what it is. We still need to know its value. So I now need you to go through your function again and this time plug in 1/3. I need to know what it is. Yeah, that's fine. Well, but it's not really half because the graph doesn't stop at 0, remember? Yeah. All right. And what do we have? A point of inflections. These are our little notes. All right. Because then we're going to go through, and we've already done part of our work here, and figure out what else we need to graph this function well. And then we'll stop and let you work on your lab. One more point. What is it? It was, no, do we have one more point? Yes, we do. 1. It was 1. I couldn't see the dash because it was a 1. Yeah. And here's what's nice. Just by looking at this sketch, you know exactly what this is going to be. This is going to be a minimum value, but you need to figure out, we know there's a minimum value at 1. We need to know what that minimum value actually is. Plug it into the function and figure out f of 1. So f of 1/3 we said was 7.1. And f of 1 is 12 minus 12 minus 12. 0? 0. Okay. This is the chart I'm talking about. This is the chart you're going to make for every problem you have to graph in 4.4. So like I said, we're doing 4.3, but we're kind of getting into 4.4 a little bit too. We're actually graphing them. We're going to finish the graphing this one, but we still need some more information. And we need information like what you learned back in algebra and pre-calculus, but I have something to help you with that. But you see this little chart I did? You're going to do that for every problem. It helps immensely. Line the chart up nicely, and we'll go through some of these examples on Thursday, don't worry. But to fully graph a function, this was so important, I actually, because I don't want you to sit there, let me show it to you so it's on the video too. From 4.4, graphing guidelines. We did a big chunk of it, and I printed them out for you so you just have them as a piece of paper too. Take these graphing guidelines. Because some of this stuff you may not remember from pre-calculus. We actually completed a few of them, but we're going to go through the list and see what we didn't complete yet and get it done, and then graph this function. I didn't trust you all to go in. Like I said, the good part is we've already done a bunch of it, but let's go through the list and see what we haven't done yet, and let's do some more. So when you graph a function fully, first thing you're going to do we have a lot of this done, but let's go through each step. First thing, identify the domain. Number 1. So everybody on your paper now, we're doing number 1. Number 1 says, identify the domain. Here's what's great about polynomial functions. What is the domain of every polynomial function? Remember what our function is. Is there any value of our original function, which was up here? Is there any value of that original function that you can't plug in for x? No. Where you need to really pay attention to domain is rational and logarithmic and trigonometric functions, which we will do examples on Thursday. Okay? We're doing the simple one today. The polynomial. All right, so domain, we're done. We know the domain. Be able to identify a domain. Exploit symmetry. Symmetry is a fun thing that you may not have remembered. Take advantage of double check real quick to determine if you have an even or odd function. So let's do that, because you know what's nice if you know you have an even function? Even functions are symmetric across what? Y-axis. That will help you graph it if everything up to the y and after the y is supposed to be a mirror image, correct? What are odd functions symmetric to? That's a great guess, but no. Y functions are symmetric. Do you know what that's called? You have it right. Do you know what it's called? He said this, which he is absolutely correct. It's the line y equals x. All right, so an even function means, I'll do a crazy. Do you see that? Even function. Odd function is, here's a classic odd one, right? That's an odd function. Okay. How do you tell if it's even or odd? Find f of negative x. Remember this from pre-calc? No, that's why we do it. why we review it real quick. Find f of negative x. So go back to your original function. This is quick to do. So it's 12 times negative x cubed minus 12 times negative x squared minus 12 times negative x, which would give me, so here's how it works. A negative value cubed remains a negative value. But a negative value squared becomes positive. Negative, negative, plus. All right. For a function to be even, I'm going to put it at the end here. That means f of x is exactly the same as f of negative x. Or let me write it the other way. It's probably better. F of negative x ends up being the exact same function. If a function's odd, f of negative x ends up being the exact opposite. Okay, the majority of the time, neither of those is going to occur. Look at your original function. The original function was for it to be the same, it's got to be positive, negative, negative, positive. Nope, not the same. For it to be the opposite, every sign has to be opposite. Is every sign opposite? Nope. So this was a good example to show you, though. This is neither. So it is not symmetric. That's what we mean by exploit symmetry. You'll be able to look at a function. If a function only has x to the even values in it and no constant, that's an even function. It's going to be mirror image across the y-axis. Okay. Number 3. So 3, 4, 5, 6. We did. That's the chart. Okay, we already did it. That's where you would do that chart. Find your first derivative, find your second derivative, and do all that. Okay, it's done. So we already did that part. Let's jump down to 7. Okay, asymptotes you're only going to look for in your rational functions. You could have an asymptote in a log function, ln function. You could have an asymptote in some of your trig functions. Okay? We do not have an asymptote in a polynomial function, so we can skip the asymptote part. But we do have something called end behavior. End behavior. Do you remember end behavior? If the highest power is even, then the ends are the same. If the highest power is odd, the ends are the opposite. Okay? So this occurs for a polynomial function. In this case, our function is an x cubed function. Highest exponent is positive x cubed term, right? Leading term is a positive x cubed term. So that means my end behavior goes like this. Okay? It's increasing. The function ultimately is increasing. If you were looking at a charting stocks, right? Stocks kind of go all funky, but you want this. you don't want the other way, right? So That's your end behavior. Even, positive, or both up. Even, I think we did this in the beginning of the semester. Even but negative leading term, they're both down. Okay. Obviously odd but negative starts up, goes down. Okay. So that's your end behavior. That gives you information. 8, intercepts. It's always good to figure out your intercepts. Okay, first of all, your y-intercept is the easiest, because to get a y-intercept, you simply set x equal to 0. So what is my y-intercept for this function? I think it's a 12, right? If you set all your x's, yeah, f of 0. So f of 0 equals 12. So it's 0, comma 12. Y-intercept's done. For x-intercepts, this is where you might need to get into those calculators a little bit. So for your x-intercept's a little bit harder with this particular function, because you have to set f of x equal to 0. So that means 0 equals, where is it? What's 12x cubed minus 12x squared. All right, good news is real quick, I can divide everything by 12, right? So you can try factoring by grouping. Let's see if that works. Factor by grouping, that would be x squared, x minus 1, take out a minus 1. This is just factor by grouping. It works. So we have x minus 1, x squared minus 1, x minus 1, x minus 1, x plus 1. Just factor it. Okay, this again goes back to pre-calculus. You've got to be able to find your zeros of a function. And what are my zeros at? So you have x-intercepts at Does anybody remember what occurs when you have a double? Does anybody remember what occurs on the graph when you have a double? This is one of those little things. Yeah, it touches it, it doesn't go through. All this stuff is good to know when you're trying to sketch a function, right? This is called a double root. When you have a double root, in pre-calc, you refer to that as the multiplicity. All right. It actually, so that means it does not go through one, it touches one. All right, so let's put everything together. Let's get it all together. Boom, we've got everything to graph this function now. Let's start. I'm gonna put in my intercepts because they're right in front of me. I know I've got something going on at here. I know when it gets there, it's gonna touch and turn. I don't know where it is yet, but it's gonna touch and turn. What else do I got? -1. And at -1 is just going through my function. And what was my y-intercept? 12. All right. So let's get those mins and max and everything else in. What did I have? I had a maximum at -1/3, 14.2. So get your put your maximum on your graph. Everybody should be graphing this right now. Put your maximum on the graph. The max value, if you look through your notes, was negative 1/3, 14.2. So it's going to be up here. I have a minimum value. You just have to go through your notes because I'm going to have to keep scrolling up and down to get all the information. I have a minimum value at 1,0, and that makes sense because didn't we say it was going to touch it and turn around? So I got a min going on at 1,0. So this is also a min. I've got a point of inflection at 1/3, 7.1. I probably didn't spread this out enough. My graph's going to look funky. But let's think about it. And my end behavior, didn't I say I was starting down and ending up? So that makes sense because I'm going to be starting down and ultimately I'm going to be ending up. It's all there with a min there, max. So let's just go ahead and sketch it now. It's going to be a little... I should have spread my ones out, but that's okay. So it's going to start down. It's going to come up. It's going to turn there. It's concave down, and then it switches. There it is. There's your graph. Not the prettiest. So we have done this with a polynomial function. We are going to do this with rational functions, which means we're going to add asymptotes. We're going to do this with other functions. I'm going to stop there for today, though, because we've gone through the whole thing with a polynomial function. We used first, second derivative test, and 4.4 is literally this list. This is all of 4.4, is getting your function fully graphed. That's where we're going to end today.